Hey, hi. Good afternoon, everyone. So I'm Abhishek and Changrong. We are from Microsoft. And we are going to talk how we are using SRv6 for our, using Sonic for our AI backend networks. OK, so before we deep dive into how we are using SRv6 with Sonic, let's first try to understand why we are building a dedicated AI backend network. So what we are seeing with the new AI workloads, the traffic pattern is very small flows, a small number of large flows, basically elephant flows that takes a lot of network bandwidth. Plus, this AI training jobs need to run on a lot of GPU workloads. So there is periodic burst of data that needs to be synchronized across multiple GPUs. So such traffic pattern is not well absorbed by a traditional front-end network, which is more adhered to a compute and storage type of traffic. So that's the reason we are trying to build a new AI backend network to make sure we can handle any congestion that can cause a drop or a packet collision that can lead to a retransmission and degrade the performance of an AI training job. Okay. So another challenge that we see with AI backend networks is since we are talking here about hundreds and thousands of GPUs that are connecting to each other. So all these AI clusters cannot be consigned to a singular DC site. They needs to be connected across different physical DCs. So that's another challenge with this AI backend network. We need to connect this geo-distributed GPUs at the scale level. So summarizing now. Okay, so talking now, what are the challenges, right? So as I said, this flows, we have a small number of large flows. So basically, with this thing, we cannot use the bandwidth of the network well because of the entropy is not that high. So we need more active traffic engineering. Similarly, to make sure we are using the bandwidth of the network in some efficient manner, we have to have a good control of the path the packet is traversing. Plus, the scale that we are looking here, we have to make sure the network is able to detect the failures at a quick rate. Especially with this scale, the failures are bound to happen. And plus, with all these challenges, we want to make sure we don't use any proprietary technology to solve these challenges. We use which is something which has been open source and which has been in the network for some time. So the solution to our challenges is we are using SRv6 for AI backend network. So the thing with SRv6 is this has been standardized for many years now with the data plane support available in most of the merchant silicon. So SRv6 being a source routing protocol helps us defining a fine-grained path, which helps us to use the network bandwidth in the most optimal way. Plus, it allows for a quicker resolution for any failovers because the sender can reroute the packet to different path. The NIC can reroute the packet to different path if any failure is detected. So basically, SRv6 helps in enabling path enumeration for traffic management and then providing fine-grained network congestion. So now I will give the mic to Changrong. He will talk about how we have integrated SRv6 with Sonic for this use case.
Yes, thanks, Abhishek. Yeah, now let me dive into some technical details about our SRv6 deployment. So first, we chose to do SRv6 with the latest standard called compress it or use it. So specifically, you want to compress all the SRv6 sits for the network path in the destination IPv6 address field. Specifically, in our case, we use 32 bits locator block, and then every 16 bits for a single node usage. So for a traditional 3-tiers network, we can fit in 6 sits, which is sufficient for a full network path that from 1 NIC to 2 BT0s, 2 BT1s, and a T2. And with use it, we can get rid of the SRh, which simplifies the hardware implementation and also speed up the deployment. And here we show a very simple example graph for how the SRv6 work in the network. So when the NIC wants to send the traffic from one side to the other side, then the traffic carries this SRv6 seed list, and that will instruct the packet to go to this 01T1 and then to another 01T0 and then to 01T1 and then to another T0, and finally reaching the destination NIC. And when we detect a congestion or the failure on the T1 by, for example, packet streaming or embedded network telemetry, then the receiver will signal back to the sender, and the sender will simply replace the usage in the IPv6 destination field that corresponds to that T1 with the new T1, and then get a new path to send the packet. And traditionally, the SRv6 control plane is very complex because it needs to use the BGP+ECMP protocol to propagate the seeds across the network. However, in our network, we want to get rid of this complexity. So our solution is to do SRv6 with static configuration. So we configure every switch with only one segment identifier. And then the switch will have static routes for every switch neighbor that it has, and also the NICs. And finally, the host will get the list of SRv6 paths that it should use from our central controller. And here I will show you a very simple example of the configuration and how we do the data plane forwarding. So here we have 3 switches. Every switch have one SRv6 seed, and we are using the UN function, which is the compressed version of the ends function in SRv6. And then for this particular switch B, we will have 2 static routes here since it has 2 neighbors, and the static routes use the neighbors use it as the prefix, and the router interface of the neighbor switch as a next hop. So when the switch A sends a packet to the switch B, the IPv6 DA field will carry this SRv6 seed list. Then you match the SRv6 seed table in the hardware, and then the switch will do a left shift and remove the usage on the top of the seed list and get this new IPv6 address field. And then this new IPv6 DA field will match the normal IP routing lookup table, and you hit the entry for the switch C and get forwarded to the switch C. So everything is very simple in the control plane and the data plane. And we implemented all of these features in our Sonic OS because it's very popular, as you can see. And we introduced 2 new tables in the configuration database in Sonic, which is MyLocators and MySeeds. And when our central controller to program these new configurations to the switches, we have a piece of software called BGP+ECMP to program those configurations to the FR, which is an open source routing software maintained by NVIDIA. And here we show a simple config snippet for the SRv6 static seeds configuration in FR. As you can see, you just need to configure IPv6 prefix, and then the locator name you use, and the behavior you want to switch to perform. Right, after we solve the challenge in the control plane, then another challenge is for us to verify that all these high-speed switch ASIC can forward and can perform the SRv6 function in the data plane at line rate. So because right now we are talking about 100 terabit switches ASICs, right? You want to make sure those high-end switch ASIC can forward your packet at the advertised speed. So how we do it? If we intentionally use enough number of traffic generators to do port-to-port testing, that certainly works, but the problem is that the traffic generators are very expensive. They are much more expensive than the switch itself. And so we built a topology called Snake to actually maximize the traffic stress on the switch ASIC with a very limited number of traffic generators. So basically what we did is that we separated the traffic generator ports that we had into 2 hubs. We connected the first hub to one side of the switch, and then the other hub to another side of the switch. Then we connected all the switch ports in the middle, back to back, to form a L3 routing domains that are adjacent to each other. And intuitively, it's very simple. However, during the deployment, we found several challenges. The first one is that SONiC inherently does not allow you to put two router interfaces in the same subnet because it causes a routing domain collision. The solution we use is actually to put first group the interfaces, and then we put them into different verbs so that we can avoid the routing domain collision. And by default, SONiC applying the same router MAC for every router interface, and that will cause the source MAC and destination MAC collision on those back-to-back interconnect. So actually, to solve this problem, we put every interface into a VLAN and customize the router MAC. And finally, we invented something very new, which is called multi-sit in the switch. Basically, we configure multiple SRv6 segment identifiers in the switch, so that when a packet traverses all those parallel links across verbs, they can select different ports within that verb, so that we can create parallel SRv6 paths in this single switch. And with all this setup, we were able to actually fully saturate the switch ASIC bandwidth with only one traffic generator in our lab. And if we do port-to-port testing, we actually need 8 traffic generators. So that's a 8x cost saving. So finally, I want to introduce a little bit about the overall SRv6 ecosystem in SONiC. Right now, we already have very mature support for the basic SRv6 UN and UDT functions. And we certainly developed the static seed allocation and provisioning mechanism in the control plane. And also, we added the static steering of traffic with the SRv6 seed list. And the BGP EVPN-based L3 VPN services has been introduced a long time back because it's an old feature in FRR. And overall, all the control plane features keep evolving with this open source FRR routing stack. And that's the benefit of using open source software. And we also have a very big community. We have hyperscalers as us and Alibaba. We also have several vendors participating in the development. And there are also other contributors that I cannot name here. But if you search online, you can see use cases across different kinds of network, including telecom and enterprise network, and in our case, cloud networks. And in order to support the SRv6 usage feature, we actually did some enhancement to the existing OCP side. So the first, we enabled the endpoint flavor control for the basic UN and UA feature. So this allows you to determine what the SRv6 module means, the ASIC, to do with the packet when it reaches the end of the SRv6 seed list. And second, we enable this seed entry next of attribute for the UA function so that we can do UA forwarding. And then we enable this side entry tunnel attribute because this is the inherent attribute inside to allow switch to do decap. And then we enable the UDT decap functions and also the USD endpoint flavor for UN and UA action. And finally, we allow the UDT function family to use this mySeed entry verb attribute. So that will allow you to decap the packet and put them into different egress verbs. And we also want to talk a little bit about the future of SRv6 in SONiC. So actually, there was a reason why we use UN for now, because it's very easy for software and hardware support, and the usage is also very intuitive. But in the future, we can foresee that there will be the addition of UA. Actually, I think the control plane feature of UA has been added to FRR, and it will be enabled in SONiC also very soon. With UA, we can get rid of the static routes and enable direct end-to-end routing support. And that also provides a more fine-grained path control because we can assign UAC to every link. And finally, we believe people will keep defining new SRv6 actions and bring it to SI and also SONiC. So generally, we encourage contributions to all areas of SONiC from all the vendors or companies. Thank you very much. That's all of our presentation.
My Mike's not on. Hello. Yeah, this is Aditya from SRv6. Congratulations on figuring out how to do snake tests on Sonic. So congrats on that. One quick question. SRv6 naturally works with IPv6. Have you thought about like its extensibility with IPv4 only fabrics and ability to use maybe MPLS, which could have been used both for IPv4 and IPv6? Did you evaluate MPLS support to do exactly what you're doing here?
So we never considered the MPLS solution because that's traditionally used in WAN, right? So we never use it in data center. Yeah, but if you have a fabric that consists of a mix of IPv6 and IPv4 traffic, that may be a viable solution.
Yeah, so just to clarify for you and for the community, just because MPLS is used for WAN doesn't necessarily mean it cannot be used for a data center. It actually fits exactly the use case that you're talking about and can also be protocol agnostic, right? You can use for V4 and V6. It can be a single solution that can work for all the use cases.
Yeah, I think for our case, the network fabric is already IPv6, so that's the point we.
Yeah.
But I think yeah,
correct.
Enjoyed the presentation. I was wondering if you could comment a bit on the like the loss detection or congestion detection mechanism and the selection of the alternate path from the source.
What do you mean by comment on that?
What are the mechanisms that you're using to detect loss or congestion
and
then specify an alternate destination?
We use packet trimming, which is an earlier presentation today. Have you checked that one?
Okay, no, that answered my question perfectly. Thank you.
Okay.
So the test you presented is open source? You can use it?
Yeah, we have an open source test plan in Sony management repo, but we are still refining it.
This load test that you showed, it's open source? Or
yeah, the snake test, right?
Stress test, yeah.
Yeah, it's open source.
Cool.
Well, a couple of questions. First, you mentioned packet trimming, but it handles congestion when the network is intact, right? Mm-hmm. With your fixed seed list, when there is a topology change in your backend network, for example, some link fail, how would you handle that failure? That's the first question. And the second one, maybe those are connected, is that when the NIC is given a list of the passes, right, which is, I guess, adjacent seed along the strings together, right? Now, the question is, how do I use, as a NIC, how do I use that? Do I map a queue pair into a certain specific path? Or is there any other choices that would you recommend? Since you have the fixed list and the NIC has to decide which path I use for which specific packet, right?
Do you want to answer this one?
Yeah, so I think the NIC is running a protocol. Basically, it calculates the metrics of all the paths that it can reach to a given queue pair. And then if there's any link failure happens, the NIC protocol will understand, okay, the metric is going bad for a given path, and based on that, it will update the entropy or the seed list for a given packet. And I think what was your second question?
Yeah, I think both questions are linked. You answered both, actually. Since the first one is there is any topology change, how would you redirect, right? If there is a link failure, a bunch of the paths is no longer useful, right? But if that basically says you put all the intelligence on the NIC to decide, hey, these paths are not useful, I'm going to use whatever left.
Correct.
Is that right?
Yes.
And then mapping the queue.
I appreciate you can take it offline. Okay. We can't have too many follow-up questions. Thank you.
Hey, hi. My name is Ratish. So I have a question on the topology you were showing. Like you have like multiple planes, and you are showing like the NIC is connecting to multiple planes, right? So do you do any hardware breakout at the NIC level to diversify the flows to multiple plane, or like is it like for multi-tenancy or something? Like why you're using multiple planes there? And do you do any hardware?
So the reason why
breakout?
we use multiple plane network, it's the same as the community. There are several literatures like academic papers or community articles to talk about why we use multi-plane network. It's not a unique deployment in Microsoft.
No, my question is like on the NIC side, do you do breakout?
Yeah, we do breakout.
Hardware breakout, which connects to multiple planes.
Yeah,
so if it is a
breakout.
400 gig, so you do hardware breakout in 200 gig into 2 and to connect to 2 planes?
So I think the exact number is confidential, but yeah, we do breakout.
Okay, got it, thank you.
So can you please explain how you are combining back to sender over SRv6?
So
how you are doing back to sender? You were showing that you are doing back to sender. So how are you doing that?
Trim neck. Do you know packet trimming that we did earlier presentation? So when the trimming happens, the receiver will simulate neck to back to the sender. And that information will, the path information will be embedded in the trim neck. So the sender will know which SRv6 path has that congestion.
Thanks for the presentation, guys. Very informative. Quick question about the SDN controller. Is that an open source controller or?
No, that's private.
Yeah. Private, and the only function there is it's just sending the static routes, or?
Yeah, do configuration, and when there's a topology change, we can also update the set list in the NIC.
Okay. Is there any plan of using an open source controller?
Not that we are aware of.
Okay, thank you.
A question on the performance. So when, let's say we have a link failure or congestion that we detect by packet trimming, in what time frame does the NIC now come up with the updated SID list? How long does that take?
1 RTT, right, in packet trimming sites.
Sure, 1 RTT to get the packet trim back.
Yeah.
But what is the time it takes for the NIC now to update the SID list for the next packets going?
Well, that depends on the vendor. Yeah. Because basically the NIC size implementation is not open source.
Sure. So in your experience, in your network deployment, what were the time frames that you guys saw?
We don't have that information.
Yeah, we don't have the right numbers.
Okay, thank you.
All right, great talk. Thanks for sharing that.
Thank you.